More examples of L'Hopital's rule, this time with transcendental functions as opposed to rational or polynomial. This time we have the limit as x approaches e of 11 natural logs of x minus 11, and then divided by x minus e. First thing, we need to verify that it does indeed fit L'Hopital's rule, one of the indeterminate forms. So let's do that. We're going to use direct substitution first. And by direct substitution, we get 11 natural log of e minus 11 divided by e minus e. Now, denominator is clearly 0. Natural log of e is 1. So we get 11 times 1 minus 11, which is going to end up being 0 over 0. And that's one of our indeterminate forms. Now that we know it's indeterminate, we can use L'Hopital's rule. So remember, I put an L in a circle to indicate that I've used L'Hopital's rule. And now we're going to take just the derivative of the top and the derivative of the bottom. Lim, x approaches e, the derivative of natural log of x. So we're going to get 11 times 1 over x. Derivative of 11 is 0. Derivative of x is 1. And then the derivative of e, not e to the x, is 0. And wouldn't this just simplify into 11 over x? So this is now lim as x approaches e of 11 over x. And by direct substitution, that is 11 over e. The only other way to verify the solution is we can't factor it, we can't rationalize it, we can't go through and do any of the techniques that we've learned before. So L'Hopital's rule is the only way to work with this, but we can check it using a calculator. Let's graph it by using a calculator. And then let's see if we get 11 over e. And by the way, 11 over e, just to verify that, 11 divided by e to the first power is 4.0466 or 67. Right? So let's just go ahead and approximate that. So it was 4.0467. So 4.0467. All right, so let's hold on to that answer as the approximation. We're going to go in our calculator, and just like we did before, we're going to verify by graphing the original function. So I'm going to zoom standard first, and that's not what the function is. We have to go to y equals. This is the one we had from before. So we have quantity 11 natural log of x minus 11, and we're going to divide that by x minus e to the first. Right? So that's the trick with the calculator. If you don't have e in there, just use e to the first. All right. I'm just verifying that I did put the parentheses in there. So I'm going to graph. And we're approaching e. Now remember, e is 2.718. All right. So what we're going to do is we're going to trace this until we get to about 2.7 or as close as we can get to 2.7. All right, so that's really close. I'm going to zoom in. Right, and we're going to trace again. Now remember 2.718. All right, so that's pretty close too. So right here, and we're going to zoom in again. All right, so right here, we're going to zoom in. Let's trace again. We want 2.718 if we can get there. So we're going to zoom in again. All right, trace 2.716, 2.719. So that's pretty close. Let's just zoom in a couple more times. And we can keep doing this all day. All right. So 2.718. All right, so that's pretty close. All right, so we get 4.4064. And remember what we got before, 4.0467. So it's very reasonable that our answers are going to be the same. But notice that calculus, we can't get the exact answer without calculus. Okay, so only from L'Hopital's. All right, so that's the power of the calculus, is being able to get those exact, those precise answers, okay? And that's what we want most times. We don't want the approximate, okay? We want the exact answers when possible. Another example. Let's go ahead and find the limit as x approaches 0 of 6 sine 2x over 7x, another transcendental example. So we're going to use direct substitution, and I think most of us can see what's going to go on with this. We're going to get 6 sines of 2 times 0 divided by 7 times 0. Sine of 2 times 0 is really just sine of 0, and sine of 0, the y-coordinate at 0 radians, is indeed 0. So we get 6 times 0 over 7 times 0, which is 0 over 0, and that's an indeterminate form. Now be careful with this one. We are going to use L'Hopital's rule, and that's going to become the lim as x approaches 0 of, now be careful, it's going to be 6 cos of 2x, but we have a chain rule. So we need to take 2x prime, and then in the denominator, we just have 7. We know that the derivative of, and it should just be like this, 2x prime, the entire quantity, 2x. The derivative of 2x is 2. All right, so that's a 2 right here. And we're just going to multiply the 6 times the 2 to get 12. So we're going to get 12 cos of 2x over 7. Let's try direct substitution, because clearly we're not going to get 0 over 0. At worst this time, we'll get 0 over 7, but that's not what we're going to get. So now it's going to be 12 cos of 2 times 0 over 7. 12 cos of 0 over 7. And in your calculator, you can get 12 times 1 over 7. The cosine of 0 is 1. All right, so be cognizant of that fact with the cosine function. Okay, so just in case you've forgotten, all right, the cosine, so right here, remember, we have sine of 0 and cos of 0 on our unit circle. All right, and right here is the point. All right, or other way around, excuse me. It's cos of 0, sine of 0. All right, and right here is the point 1 comma 0. So the x value at 0 radians is 1. All right, so just reminding you of that trigonometry that's going on there. Clearly 12 times 1 is 12, and we end up with 12 sevenths. All right, so hopefully that's a little bit helpful as to how to go through, work with the transcendental functions to be able to use L'Hopital's rule, and then to check your answer by using your calculator. All right. As you probably suspected on the examination or in examination, I'm going to ask you for precise answers, not the approximate answers. So this is where you want to make sure that you're comfortable using L'Hopital's rule. In the next video series, we're going to take a look at what happens if we have to use L'Hopital's rule multiple times to find the limit of a function precisely.